Okay, now let's use the results of the derivation to see if Joe Kittinger really was in space and how these circumstances were at this extreme altitude. And for this we will make an example calculation, and this will show you how to use the different layers of the standard atmosphere, which will be shown in the next video. In this clip we will actually use the standard atmosphere equations to calculate the pressure, density and temperature at the altitude at which Joe Kittinger jumped from the balloon. And we see on the right side here of the slide, we see Joe Kittinger jumping out of his balloon, a bit of fear, and then making his record jump from 31,333 meters down to a number of layers and until he arrives safely at sea level. For our calculation, we're going to travel in exactly the reverse way. So we will start at sea level, and then we will jump through all the layers to arrive at the altitude where Kittinger jumped. Luckily, he's just below the 32 kilometers, which is why I chose to do this example, and you can do the one with Baumgartner, which is just above the 32 kilometers, as a follow-on exercise in which you can use these results and continue to an even greater altitude. So how do we do this? Let's start with the first layer, the troposphere, which starts at 0 kilometers and goes up to 11 kilometers. The gradient there is minus 6.5 Kelvin per kilometer. So in SI units, it is minus 0.0065 Kelvin per meter. So let's start by first jumping to 11 kilometers. The temperature. T1 is given as T0 plus A times the difference in altitude. In this case, as start value, we use the sea level values, which are given. T0 is 15 degrees Celsius, which is 288.15, is what it says, Kelvin. The lapse rate was given, Kelvin per meters. So using this with Toussaint's equation, we can calculate the temperature at the top of the troposphere. Times 11,000 minus 0, and this equals 216.65 Kelvin, which is our T1. Now, from the equations for the layer, temperature gradient layer, we know how to calculate the pressure once we have the temperature. And that's this equation which we derived in the previous clip. Minus G divided over AR. And for this we have everything. We have the T's, we have calculated these. We know the start value. We use the sea level value for this, which was given in a table. And we know these constants. What do we use for these constants? We use a G, which is slightly more precise than the 9.81, which we often use. We use the 9.665. These powers are very sensitive to significant digits. So also for all the intermediate values, I will memorize or write down a lot of digits to make sure that we carry on with maximum accuracy. For the R, there are in fact different values which are sometimes used. We have chosen to use the 287.00 joule per kilogram Kelvin as our specific R. Sometimes you see 287.05 being used, and if you use that value, you will get the exact values from the table which you often see for the standard atmosphere. But in our course, we consistently use the 287, which to our knowledge is the best value right now, even though obviously there is a choice of what you choose as a mixture of the air and hence the molar mass. But in our calculation, it's important to remember that we will use these values. Well, if we then write down our equation, P1 is then T1 6.6265 divided by T0 to the power G divided by R, or actually A, I wrote the first time, but okay. Then I have to put A in here, like this. And we see two minus signs, so they cancel each other out. And we have to multiply this times our starting pressure, P0, which we have moved to the other side of the equation to calculate our P1. Well, filling this in gives us, and if you actually compute this, it's often a good idea to first calculate the exponent to reduce the errors, because for the troposphere this exponent always has the same value, and this is 5.25648. And of course for the density it's one less, it's 4.25. But this is a trick to memorize this value to make sure that you're on the right track and you have done the units right. Well, if we calculate then everything with the values in there, we will get our first pressure, P1, 5.79149. Many digits, just to be safe. And now simply using rho equals P divided by RT gives us our density. So we don't even have to use the other equation for density. We can simply use the equation of state. And this will be, if we fill in the one value for every one of them, it will be 0.3638. And what else is I have there for numbers? 84193, etc. Kilogram per meter cubed. Running out of space here, but I don't want to make a new page for this bit of the layer. So now we have moved to this altitude. We have stepped to 11 kilometers and found these values. The next step is to make sure that we carry on in the direction of 20 kilometers. So basically we're going to do the same, but we see in the second layer that we have an isothermal layer. Let's first copy the values which we had at the start. So we had T1, I'll use a different color. T1 we had at the start is 216.65 Kelvin. P1 we had as a start value, our start value for this layer, 22625.79149. And now we have a layer where the lapse rate is 0, which means that our second temperature is the same as the first one, is 216.65 Kelvin. So we're quickly done with the temperature. And now the pressure, we have to use a different equation now, and we have to use the right index as well. 2/1. Not very neat, is it? P2 over P1 equals e to the power minus g divided by RT times H2 minus H1. It is simply as filling in the value again. P2 is e to the power minus 9.665 divided by 287.79149. times 216.65 times the altitude, which is 20,000, again in meters, minus 11,000. And this all times the starting pressure, which was 22625, and then a little bit more behind the decimal. If we calculate this value, fill in all the numbers, you should get 5471.9, and depending on how accurate you saved your numbers behind the decimal, it might be different. And again, using rho equals P divided by RT, we can now also calculate our density, which is already quite low, 0.088039 kilograms per cubic meter. So let's look at these values. Do they make sense? This value of P, 5,000 Pascal instead of 100,000, which we started, so it means about 5% of what we had. And this value, 0. It's already not very much, so we're already quite high in the atmosphere. And what did we do? So we jumped here, and we're currently at 20 kilometers, which is higher than most aircraft fly. And you can see why. There's hardly any air there. We have to make one final jump, and now we are again in a gradient layer where there's a positive gradient. Will the equation still work then? But because pressure always has to reduce when you go up. Let's have a look what happens there. Our start values we have to copy, of course, again. So our start values are now P2 equal to 5471 point something, 3502 Pascal, and our density, our temperature is what we need actually. Our temperature T2 was the same throughout the complete layer, was 216.65. Now we have a gradient layer, so what equation do we use? P1, no, it's not P1 this time. We're going to step to altitude 3. So let's call it P3 over P2 equals T3 over T2 to the power minus GAR. Filling in the numbers. P3. Well, T3 is the first thing we need. We haven't calculated that yet, so let's calculate that. It's 216.65 plus 1 Kelvin per kilometer. So plus 0.001 times 31333 minus 20,000. And this gives us a temperature which is higher than the previous temperature, obviously, as the temperature is increasing. And it is actually not that much higher, 227.983 Kelvin. But still better than the stratosphere, where it was minus 55, 56. Now it's a comfortable minus 45, which I once experienced in this upstate New York as well at sea level. So comfortably warm relative to the stratosphere. Then P3, now we can calculate, we fill in the numbers, 227.983 divided by the starting value for the temperature to the power minus 9.8065 divided by 287.0. And now it's a positive lapse rate. So our exponent becomes negative, but our complete set of the division of temperatures T3 over T2 become larger than 1, so it all works out. Multiplied by the start value 5072, which gives us the temperature at the altitude where Joe Kittinger started his jump, the pressure, I should say the pressure at this altitude, and which is 958.295 Pascal. And using the equation of state, we can also calculate at this altitude the density, which is also incredibly low, 0.0146 kilogram per cubic meters. So let's look at these values at the altitude of Joe Kittinger. The pressure P3 is 958 Pascal, which is less than 1000 Pascal, which means that it's less than 1% of the sea level pressure. And this means that 99% of the atmosphere was actually below him. And looking at both the pressure and the density, I think it is not unreasonable to say that he was really nearly in space, on the edge of space. And in fact, he experiences himself. I think Joe Kittinger clearly showed how great the human body can adapt to all kinds of situations. Because he once, during this the highest jump, he had a hole in his glove, but automatically his finger swelled to twice the normal size and in this way closed the hole in the glove, and he was saved in this way. Okay, so we looked at Joe Kittinger, but Baumgartner went even higher. So for you as an exercise, I leave it up to you to start at 20 kilometers altitude and then go to 32 and then to the altitude of Baumgartner at over 38 kilometers. And then find out what the pressure and density were at those values. So that's a good start, and I wish you success with this exercise.